All right, this is the review for Unit 3. These questions come from Chapter 4. Really, there's three main topics to be prepared for the test for Chapter 4 or Unit 3. You need to be able to take the derivative of exponential functions. This one here, question 1, this will be, more of a basic one. As far as being prepared for the exam, something like question 3 here or question 4, a little more complex. The second thing you need to be prepared for is to take the derivative of the natural log function, something like question 2. Again, question 2 is a little more basic. If you look at page 2, question 7 or question 8, where you're using properties of logarithms, that's more along the lines of being prepared for the exam. And then really the third thing starts on page 3, being able to solve application problems involving exponential functions. So just some things to think about. Now, starting here on question 1, the derivative of the exponential function. The rule to keep in mind here, if you're taking the derivative of e to the u, then it's just simply e to the u times u prime. Let me rewrite that, e to the u times u prime. So what we have here the derivative of e to the 2x squared is simply e to the 2x squared, and now we need u prime, where u is 2x squared, so u prime would be 4x, and usually this term here, the 4x, would multiply in front of the exponential term, so I'm going to rewrite this as y prime equals 4x times e to the 2x squared. Now, like I said, this is a pretty easy problem. You can expect more difficult problems on the exam, but this is just kind of getting you prepared, more so reviewing the rule of differentiation for the exponential function, which is the derivative of e to the u equals e to the u times u prime. Now, switching over here to question 2, there's a rule involving the derivative of natural log. So the derivative with respect to x of the natural log of u is equal to 1 over u times u prime. So for this example, question 2, we have y prime. Now this expression right here, the 4x squared, this is like u. So this is the natural log of u. So according to this rule right here, the derivative of natural log of u is 1 over u, in this case 1 over 4x squared. Now we need the du, or the u prime. That's going to be 8x. So this can be rewritten as 8x over 4x squared. And simplifying, you would get y prime equals the natural log, or sorry, y prime equals 2, because the 8 and the 4 cancel to a 2 over x. Now there is, well, we'll keep it like that. There is another way this could have been done. Could have used properties of logarithms, but I'll save that for question 7 or question 8 to use properties of logarithms. Now, question 3 involves an exponential function here, but it's also a product because we have the product of a polynomial, so this is going to be a product rule primarily. So if we think about splitting the function down there right in the middle. The product rule is f prime g plus g prime f, so this could be like our f function, that could be our g function. So then y prime, if we follow the product rule, would be f prime times g plus g prime times f. So f prime, that's going to be the derivative of this exponential piece of the function, and the derivative of an exponential is that exponential. So it's e to the 2x cubed times u prime, so that's going to be 6x squared. So that's f prime. Now we need to multiply that by g, so that's 3x to the 4th plus 4. Now we need to add. I'm just following the product rule from up above. Now we need g prime. G prime is the derivative of that piece of the function, so that's going to be 12x cubed. And now we multiply that by f, which is e to the 2x cubed. So now we need to look at common factors. This plus sign here kind of separates the problem into a left side and a right side. We got to think about what common terms the left side and the right side have. So I can see an e to the 2x cubed as a common term, and I can see a 6 that can be factored out and an x squared that can be factored out. So if we factor out our common terms, I'm going to factor out a 6 x squared and an e to the 2x cubed. Now if that's the term that's been factored out, on the left side, that's going to leave this term here, the 3x to the 4th plus 4. And then from this side of the equation, if you factor out the 6x squared from 12x cubed, that's going to leave a 2x. And that's about as simplified as we can make that expression. So coming over here, question 4, this is going to involve the quotient rule. Now the phrase I've been using in class for the quotient rule is low d high minus high d low over low squared. So y prime, we've got low, which is the bottom function, 5x to the 4th. So there's low, now we need d high. D high stands for the derivative of the top function. That's going to be e to the 2x to the 5th times u prime, which is going to be 10x to the 4th. So we've got low d high. Now we need to subtract high d low. The derivative of the bottom function is 20x cubed all over low squared. Now if we look at the numerator, this minus sign here in the numerator separates the numerator into a left and a right side. We need to consider what each side has in common. They definitely have an e to the 2x to the 5th in common, and there's a 10 that we can factor out of that 20, and an x cubed we can factor out of that x to the 4th. So if we factor out a common term from the numerator, it's going to be 10 x cubed e to the 2x to the 5th. And if that's factored out as a common factor, then on the left side here of the numerator, we still have that 5x to the 4th plus 4, and there's a leftover x here that There was a leftover x right here that needs to be included. So these are the terms that are left over in the left side of the numerator. Now from the right side, we already factored out the e to the 2x fifth, and we factored out the x cubed, so there's a 10 that we factored out of that 20, so that's going to be a minus 2 all over 5x to the fourth plus 4 squared. So all that's left to do is to simplify that there in the numerator. So we got the 10x cubed e 2x to the fifth. We're going to have 5x to the fifth plus 4x minus 2 all over 5x to the fourth plus 4 squared. Okay, question 5 is another application of the quotient rule. This one's a little trickier to simplify, so make sure you're watching all the steps. It's the same quotient rule. It's low d high minus high d low. So we've got low times d high minus high d low. So the derivative of the exponential right there is that exponential itself, e to the 2x cubed times the derivative of the exponent, which is 6x squared, all over low squared. So this is e 2x cubed squared. So we need to, just like with the last problem, factor out some common terms from the numerator. This minus sign separates the numerator into a left side and a right side. So both sides have an e to the 2x cubed. Here's an x here that we can factor out of both, and between a 4 and a 6 we can factor out a 2. So we're going to factor out a 2x e to the 2x cubed. That's going to leave a 2 from the left side from that 4 right there. And then it leaves an x here and a 3 there, so it's going to leave a 3x and then the 2x squared minus 5 all over e to the 2x cubed squared. So if you distribute the 3x here, oh, and at the same time, something else to consider. Here we have an e to the 2x cubed that's been factored out, so now it can simplify a term in the bottom. Here we have e to the 2x cubed, and there's 2 of them because it's being squared. So this e to the 2x cubed is going to cancel with one of them on the bottom. That's also something that needs to be simplified. So y prime is going to be just simply 2x in front of the parenthesis. And we have 2 minus 6x cubed plus 15x over e to the 2x cubed. Okay, finally here, question 6, page 1. There's another product rule. We have the product of We got 3x to the fourth multiplied by e to the 5x squared. So we think about that as an f function and that as a g function. Then we can use the product rule, which says y prime equals f prime g plus g prime f. So then the f prime part, this part here, is going to be the derivative of this 3x to the fourth, which is 12x cubed. So there's f prime times g plus, now we need g prime. That's going to be the derivative of this exponential. Remember, the derivative of an exponential is the exponential term multiplied by the derivative of the exponent. Now we need to multiply that by f. Okay. So we have y prime equals 12 x to the third e to the 5x squared. And if we combine that and write it in front of the exponential, we're going to have plus 30 x to the fifth e to the 5x squared. Now looking at terms that can be factored out, we definitely have an e to the 5x squared in common. Between 12 and 30, you can factor out a 6. And between x cubed and x to the fifth, you can factor out an x cubed. So the common factor is going to be 6x cubed e to the 5x squared, which is going to leave 2 plus 5 x squared. Well, I wrote that parenthesis a bit far. Just 2 plus 5x squared is left over. All right, page 2, we're taking the derivative of natural log functions on questions 7 and 8. Before taking the derivative, however, you're going to want to simplify these natural logs into easier forms to work with. So for this one, I'd recommend we separate this logarithm into several logarithms. What I'm going to do first, though, is take this exponent and apply it into the fraction. So this will be the natural log of x to the ninth over 5x to the fifth plus 4 to the third power. Now, since we have a quotient, we're taking the natural log of a quotient. We can use the quotient rule, which says y equals natural log of the numerator, x to the ninth, minus the natural log of the denominator. And then apply the power property to bring those exponents down. Now we can start taking derivatives. So y prime, this 9 right here is a coefficient, so it's going to stay a coefficient. Remember the derivative of the natural log of x is 1 over x. This 3 here is a coefficient, so it's just going to stay coefficient. And the derivative of the natural log of an expression here the derivative of the natural log of u, where this is u, is going to be 1 over u times u prime. So times 1 over u times u prime, that's going to be 25 x to the fourth. So then combining a few things over here, 3 times 25, 75. X to the fourth over 5x to the fifth plus 4. And question 8, similar thing. First, we're going to have to separate the natural log into smaller natural logs. It'll be easier to differentiate. So we've got a product right here. So we can separate that product using the product property of logarithms, natural log of x plus natural log of 2x plus 3 squared. And then again, we can move that exponent of 2 down. And then we can differentiate. For here, the derivative of natural log is again 1 over x. This 2 here is a coefficient, so it's going to stay a coefficient. The derivative of the natural log of u is 1 over u. So 1 over 2x plus 3 times u prime. And then simplify. Okay, the directions here to find the slope, or find the equation of the line tangent to this function at the given point. We need to write in slope-intercept form. So we need to write, remember slope-intercept form is y equals mx plus b. Now we've been given a y and an x to use from this point right here. That's where we get our y and our x. We don't have a slope, m. The slope is found from the derivative at this x value right here, x equals 2. So first we need to find y prime. The derivative of e to the u, where this expression here is u, is e to the u. So e to the negative x plus 1, now times the derivative of the exponent, which is negative 1. So y prime equals negative e to the negative x plus 1. Now, when x equals 2, y prime, we're going to plug in a negative 2 right here for, or sorry, a positive 2 for that x. We're going to get negative 2 plus 1, which is negative 1. So we get negative e to the negative 1, or negative 1 over e. There's our slope. So I'm going to call this, rather than y prime, I'm going to say, all right, slope m equals negative 1 over e. So that's what's going to go here for m. And remember, our x value can go there, our y value can go there, so that we can find the y-intercept at the b value. So y value of 1 over e equals our slope, negative 1 over e times our x value of 2. And then solve. We get b has a value of 3 over e, which means our equation is y equals our slope times x plus our b value Okay, question 10 may not necessarily have been exactly like one of your homework questions in Chapter 4, but it does apply principles that we learned in Chapter 4, plus a few things that we're still struggling with from Chapter 2, implicit differentiation. We're trying to find dy dx, so we're differentiating with respect to x, but our equation is defined in terms of x and y. So we do have to use implicit differentiation. We got a couple things here. We got a product property there, 4x times y. And we've got the natural log of a product, x squared times y, so we're going to have to expand that product right there. That's what I'm going to actually do first, is worry about this product and expand it. So I'm going to rewrite this as 4xy plus the natural log of x squared plus the natural log of y equals 7. So this natural log got split into those two natural logs. Okay, and we can take this 2 and move it down in front, so 4xy plus 2 natural log of x plus the natural log of y equals 7. Now when we take this equation and differentiate with respect to x, that has to happen to every single piece here. This first piece is a product, 4x times y, so we're going to have to use the product rule of differentiation there. If we think about this as an f function and that is a g function, then we need f prime g plus g prime f. So f prime is going to be 4, f prime is 4, then times g plus g prime. The derivative of y with respect to x is dy dx. So there's g prime times f. So these two pieces here is the derivative of that first part, 4xy. Now we need the derivative of this part, 2 times the natural log of x. Well, the 2 is just a coefficient, so it stays a coefficient. The derivative of the natural log of x, just 1 over x. So that is the derivative there of that piece. Now, the derivative of this piece, natural log of y, since we're differentiating with respect to x, we need to treat y as a function u. So it's the same as the derivative of the natural log of u, which is 1 over u times du. So that's going to be dy dx. And then the derivative of 7 there is 0. Now these terms that have a dy dx, we're going to keep on the left side. These terms here that have no dy dx need to move to the right side. So I'm going to subtract a 4y and subtract a 2 over x from both sides. So then I'm going to have dy dx times 4x plus 1 over y dy dx equals negative 4y minus 2 over x. Now, now here on the left side, I'm going to factor out the dy dx that's common in both terms. And then need to divide by this term to get dy dx by itself. So dy dx equals negative 4y minus 2 over x over 4x plus 1 over y. Now, I'm okay with that form of the answer. However, technically when you have a fraction inside of a larger fraction, you're supposed to simplify down a little further. This wouldn't be the form of the answer you'd see in the back of a textbook. What I need to do is combine this and combine that. So this one up here in the numerator, to combine that, the only way to subtract this is to have a common denominator, so I need to multiply this by x over x. So now it's negative 4yx over x minus 2 over x. So that's negative 4yx minus 2 all over x. Now I need to do the same thing to the denominator. In order to add these two, I need to multiply by y over y, so that denominator becomes 4xy plus 1 all over y. Now this fraction bar really means divide, and when you divide two fractions, you can multiply by the reciprocal here. So I'm going to change this to a multiplication problem, so negative 4yx minus 2 all over x multiplied by the reciprocal here of y over 4xy plus 1. Now multiplying that together, numerator to numerator, denominator to denominator, we get negative 4y squared x minus 2y all over 4x squared y plus x. Okay, for these application problems in chapter 4, the key phrase here is the rate is proportional to. We talked about at the end of chapter 4, a function whose rate of change is proportional to the amount remaining in that function at any given time can be modeled by this function where c is an initial amount, k is relative growth rate, and t is time. So the question in here, number 11, what will the population 8.3 years from now be? That's a future amount, so we're solving for the variable y. If that's the case, we need to be given an initial amount and a growth rate and a measure of time. We have to have all three of these variables in order to solve for y. Well, we have several statements for time, 6.9 years ago or 8.3 years from now. There's no mention of any kind of growth rate for k. So that's our first task, is to solve for k. Now in order to solve for k, we need to know three of the other variables. We need to know y, we need to know c, and we need to know t. So if we use this phrase right here, if the population was 786.9 years ago, and the current population is 1064, so if we say the initial population is 780, then the future population is going to be 1064, and that happened in a period of 6.9 years. The only remaining variable is k. So if we solve this, then we have And then to get k by itself, we're going to use a natural log. This means that k equals a natural log of 1064 divided by 780, all divided by 6.9. And this is approximately 0.045. So now that we know the value of k, we can go back and use this formula again. But now for c, we can use our current value of 1064 for the population to try to find future population 8.3 years from now. So future population y equals 1064 times e, and remember k is 0.045, and then the value of time is 8.3. So when this is plugged into a calculator, we get around 1,549, or sorry, 1,545. Now it doesn't come out to be exact, but since we're talking about a population, it's a discrete number, we're not going to use decimals. Okay, question 12. We have the same formula here, CE to the KT, because we have this phrase, it's cooling or decreasing at a rate that's proportional to an amount. One little difference here, it's not just this formula CE to the KT, we also have the ambient room temperature, which is 20 degrees Celsius. So we've been given the K value there, and since the temperature is cooling, it's decreasing, this needs to be a negative value. Okay. And then the current temperature of the coffee is 73.3 degrees Celsius. Now that doesn't necessarily transfer over to the value of C. The value of C in this case is a value when time equals 0. So here's what I mean. The temperature when time equals 0 is equal to 73.3 degrees. That's equal to CE to the negative 0.036 times 0 plus the ambient room temperature here in the formula, which is 20 degrees Celsius. Now, this exponent here is 0. E to the 0 power is 1. 1 times C is C. So this reduces to 73.3 equals C plus 20. Subtract 20 on both sides, so C equals 53.3. Now, in how many minutes will the coffee cool to 42? So they're asking in how many minutes. We're solving for time. Will the coffee cool to 40.2? So that's our future temperature. 40.2 equals 53.3 E negative 0.03, and we're going to call this T, and that's the value we're solving for. plus 20. So to solve for t here, we need to get this exponential by itself. So subtract 20. 20.2 equals 53.3 e to negative 0.036 t. Divide by 53.3. So then 20.2 divided by 53.3 equals e to negative 0.036 t. Now if you take a natural log on both sides, and then divide by negative 0.036. So time, the value of time is equal to natural log of 20.2 divided by 53.3 divided by negative 0.036. If we type that into a calculator, we get 26.95, or roughly 27 minutes. All right, number 13. Same as before, this phrase here, there decays at a rate proportional to the amount remaining. Means it can be modeled by this function. So in how many years is the question? In how many years is a measurement of time? So we're going to be solving for time in this. We haven't been given a relative growth rate k. So much like question 11, we got to solve for that first. So right now, we're going to set up an equation where we're going to solve for k. So we're going to use this first piece of information right here. The initial amount was 1,485.8. And then after 5.3 thousand years, that diminished to 103.7. Now, if we solve this for k, that'll give us a relative growth rate. So, just doing some algebra here. And then, if we take a natural log on both sides, natural log is going to cancel e. So we've got natural log 103.7 over 1,485.8 equals 5.3. Okay, now if we divide by 5.3, we get a value for k to be natural log of 103.7 Now if we plug that into a calculator, let's see what you get. This is negative 0.5023. And the reason the relative growth rate is negative is because our amount is diminishing, it's decaying. So now that we have k, we can go back to this function. Okay, and it's asking in how many years will the mass diminish to 10.8? So 10.8 is going to be the future amount if we start with 103 and use our new relative growth rate of negative 0.5023, and we're solving for how long it's going to take, so we're solving for time. Now again, just using algebra here, and then I want to get rid of this e, so I'm going to take a natural log. Natural log is going to cancel the base e, so the natural log 10.8 over 103.7 equals negative 0.5023t. Now divide by negative 0.5023, and we get the value for t. So plug this into a calculator. And we get t is about 4.5, and remember that's in thousands of years, so that's 4,500 years.